everyone, welcome back. In the previous class, we derived the formula for the solution of the wave equation in 3 dimensions. Okay, so let's again look at the formula and try to understand some qualitative properties of the solution looking at that formula. Okay, so this was the formula we derived for the solution where phi and psi are the initial conditions. U of x0 is phi of x and u sub t x0 is psi of x. Okay. So compared to the n equal to 1 case, so where it was that D'Alembert's formula, so it was very easy to verify that u given by the D'Alembert's formula is indeed solution of the wave equation, and in case n equal to 3, this is called Kirchhoff formula. It is not very straightforward to see that u is solution of the wave equation, so this is formula for t positive. Okay, so it requires some computations. They're not difficult, but one has to do that. Okay, so for example, it is sufficient to verify this first part. Okay, so this first part is a solution of the wave equation. Okay, so that's sufficient for the following reason. Okay, so if u is a solution of the wave equation, then if u is sufficiently smooth, so we can take any number of derivatives with respect to x and any number of derivatives, provided u is smooth enough, is also a solution. Okay, so that so it's sufficient to verify this one because this is just d by dt of a similar term. Okay, so that proves that u is a solution. So that first one requires some computations. I am not going to do that. Okay, so let's now look at some of the qualitative properties coming from this solution. Okay, so as I commented just now, this formula is called Kirchhoff's formula. So for classical solutions, we require this solution to be C2. Okay, and this formula tells us when that u is C2. So this is the first observation. Okay, so you can state this as a theorem. So if the initial condition phi belongs to C3 and psi belongs to C2 of R3. Okay, so we are just in case n equal to 3, so let me just repeat that, because for n bigger than 3 the formula differs. Okay, so this if so remember again, so ux0 is phi of x and utx0 is psi of x. These initial conditions. So if phi is a C3 function and size a C2 function in R3, then it's guaranteed that this function u defined by this formula, Kirchhoff formula, is a C2 function, and then one verifies that it is indeed a solution of the wave equation. Okay, so we see that, so we require more smoothness, so we require phi to be C3 for example in order to obtain a C2 solution. Okay, so this is referred to as loss of regularity. This we have already seen in some cases earlier also. In this case, it's also referred to as focusing effect. Okay, and this loss of regularity in general will create problems when we want to apply this linear theory to prove existence of solutions to the nonlinear equations. On the other hand, okay, so that's uh, the qualitative behavior as far as smooth solutions are concerned. If you consider this energy at time t, okay, so this by definition E of t, before that, so in if you look at n equal to 1 case, compare n equal to 1, okay, so it's important, okay, n equal to 1, there is no loss of regularity. But this loss of regularity persists when you move to higher dimensions. So in comparison, if you look at this energy, which is defined by half this integral over R3, we are just dealing in R. So see, this same thing is also true for Rn. So ut square plus c square grad u square mod grad u square dx. Okay, so these are functions of x and t. So we are integrating only with respect to x. So that's a function of t. So that's energy at total energy at time t. Okay, provided these integrals are finite. Okay, so then a simple computation show that, so this we did for example n equal to 1 case, so we can just use the wave equation and show that dE by dt is equal to 0. The same computation, so whatever we did for n equal to 1, so you simply take the differentiation under the integral sign and then do some integration of parts and use u satisfy the wave equation and conclude that dE by dt is 0. That means E is as a function of t is a constant, and so that's to say that the total energy is conserved. So it's the same for all t. So whatever energy we start with, so that E0 comes from the initial conditions and that will remain finite. Okay, and this is a good norm to work with. So in fact many even linear problems with variable coefficients and even some non-linear equations, when one is trying to prove uh, existence of solutions, such norms will be used. Okay, and similar to the n equal to 1 case, now we discuss again domain of dependence, range of influence, etc. Okay, so that's, so for t bigger than equal to 0, again look at the Kirchhoff formula. Okay, so take any t positive, so the value of the solution u at xt depends on those values of y which are lie on this sphere. Okay, if they lie outside this sphere, they do not contribute to this surface integrals, so they do not count. Okay, so that is the domain of dependence. So the value of the solution u at xt depends on the values of the initial data only on the surface, this SCT. Okay, so these notations we have already introduced even in the first part, so just recall that. So this is the sphere centered at x and radius ct, which also is denoted by the boundary of this ball centered at x and radius ct, and that is the explicit definition of the sphere. Okay, so this is sphere. Sphere. So center x and radius ct. Okay, so you can see, draw some pictures. So this is a t equal to 0 plane, that is just the space, not plane. So this R3, and if you take any t positive, so the value here depends only on this. So this is yes, CTX, the one in the blue color. Okay, so that's the only the sphere, not the interior. Okay, so that's important. That's important. Later on, we see in n equal to 2, this is not the case. So it depends on the entire ball. Okay, so this is the domain of dependence of this point xt, t positive. Okay, and range of influence, so it's the reverse phenomena. So a point in the uh, initial space t equal to 0, where all that can influence the values of u of xt, for which x it can contribute something to the value of ext. So that is the range of influence. And again, looking at the Kirchhoff formula, so this depends only on this sphere again. Okay, so this y should lie on this sphere, okay, at any x. So if y does not lie on this sphere, then it will not contribute to the value of ext. So this range of influence is again a sphere, okay, at t equal to 0. So this is the t space and this is the sphere. So this is again. So this is set of all so this you can just simply write this sphere. Yes, but there is a t also, so it is not just center is fine, but there is a t. Okay, so t positive. Okay, so that's the range of influence. So now, like just similar to n equal to 1 case, so now we also discuss the fundamental solution. A word of caution here, in this n equal to 3 case and n equal to 1 case, and in general uh, for any n. Okay, so this is not the full picture of, not the full picture. Okay, so that you should bear in mind. For the region, so here we have concentrated only on the x variable, and t uh, we are not uh, considering in that detail. Okay, in order to apply Malgrange-Humphreys theorem, okay, to get the fundamental solution, we have to work with not just with respect to x variable, but also with t variable. Okay, so the operator is, as you recall, so this is the wave operator. Okay, so there is both x and t variable, so we have to consider this Dirac delta function with respect to both x and t, and that makes uh, computations more difficult, and since we have not developed uh, any topics in that, so we'll not go into that. So the main aim here is to represent this Kirchhoff formula again, and n equal to 1 case again the D'Alembert's formula as a convolution. That's the, okay, so the main aim is, so representation of solution of the solution as a convolution, very similar to what we have done for the Poisson equation and for the heat equation. Okay, so only for that purpose we are introducing this simple form of the fundamental solution. So this is not the full fundamental solution, so that requires little more work. Okay, so introduce this function kw again dot t. So in case n equal to 1, it was characteristic function of an interval depending on t, and in this case it's again a characteristic function, but not an interval but a sphere. So okay, characteristic function of the sphere at the origin, center at origin and radius ct, and you are dividing that by the surface area. Okay, so this is surface area. N equal to 3. Okay, so we'll come to the general case later on. Okay, so explicitly written, so this kwxt is 1 by 4 pi c square t square. So n equal to 3, that is what the surface area is, and this is, so if x belongs to this sphere, then it is 1. So if mod x equal to ct, so that is the sphere, 0 otherwise. So it's a characteristic function, and then it's easy to verify looking at the Kirchhoff formula. The solution can be written indeed as a convolution. Okay, so this so this part comes from the data psi, and this part comes from the data phi. Okay, so that is the just main aim of introducing this thing. So we can write the solution as a convolution. Okay, so that's the main aim. Okay, so this if you look at Kirchhoff formula again, so there is a derivative term, so that we can now expand and write it. That's also useful. Okay, so consider that term which is the first derivative of this Tm phi. M is the spherical mean function, and that is simply m phi xct, and t d by dt of m phi xct. Okay, and again you use the definition of the spherical mean function. Okay, so again there is a t here, there t here, so again change of variable makes it t only in the integrand, and that is easy to differentiate, so we can take this d by dt inside the integral. Okay, and when you do that, so you get this nice formula, and again you change the variable x plus ctj to y, so you get this. Okay. So the Kirchhoff formula can also be written like this, so without derivative. Okay, so this, there is no derivative involved here. And from here also you see that, so since there is already first derivative of phi appears in the formula, so if you want u to be c2, we want phi to be c3. Okay, though these two terms just require c2, but this one requires phi to be c3. Okay, so same thing. Okay, so this is, now there is no derivative at all. Okay, and now we discuss an interesting qualitative property of this solution in 3 dimensions, and this is known as Huyghens principle. Okay, so it concerns with, so suppose you take phi psi such that, okay, support, their support is contained in B rho. Okay, so support, just recall support of a function in, so set of all x, whichever space you are, f is defined, so fx is not 0, and you take the closure. Okay, so support is always a closed set. So such functions are called functions with compact support, so because this is a compact set, and we would like to study what happens to the support of the solution at a later time t positive. Okay, so that's the main idea behind this principle. Okay, so start with this phi and psi smooth functions, so for example c3 and c2, which have also support in this b0 bar. Let me put that doesn't matter. Okay, so the first claim is, so you pick any point xt, x in R3 and t positive. The first claim is this u the solution of the wave equation with this dot phi and psi, which have support in this closure of this path. So uxt is 0 if mod x, that norm x, is bigger than rho plus ct. Okay, so that's the first claim. Okay, so that immediately implies one part, so support of u as a function of x. Okay, so t is fixed, is certainly contained in this rho plus c. So if the initial data is supported in a ball of radius rho, so at a later time t, the support of the solution is contained in a slightly bigger ball, that rho plus ct. Rho is replaced by rho plus ct, and this is the region. So this c is called speed of propagation. And this claim follows from understanding the range of influence. Okay, so the value of u of xt, this we have already seen, may be non-zero only if norm x minus y is ct for some y in b rho 0 bar. Anyhow at bar it is 0. Okay, doesn't matter. Okay, that is, this follows from the range of influence, and phi and psi are only non-zero in this, their support is here, so at most they are non-zero only here in b rho 0, closer of that. Okay, so if this condition holds, if norm of x is bigger than rho plus ct, so we should show that any y sitting on the sphere centered at x lies outside this closure of this ball. So if we are able to show that, then that will not that will only contribute uh, zero value to this solution, and that claim is proved. Okay, so if norm x is bigger than rho plus ct and y sits on this sphere norm x minus y equal to ct, then so this is simple triangle inequality. So norm of y is equal to norm of x minus, so I rewrite that x minus y minus x, and that is bigger than or equal to norm x minus norm x minus y. So this is just by triangle inequality, and now we are assuming norm x is bigger than rho plus ct and y sits on this sphere, so that is minus ct. So this norm y always bigger than rho, so phi and psi are 0 there, so uxt is also 0. Okay, so that's what is the claim. Okay, but more is true, that's what we will. So the support is still smaller than this. Okay, so that's what we want to show now. So pick again any x in R3 and t positive large enough. Okay, so what is that large enough, we'll see in a moment. Okay, again you consider any y on this sphere, because that is the point where uh, the initial data influences the value of v of xt. Okay, so if norm y minus x is ct, that is y sits on that sphere. So again by triangle inequality, so norm y is bigger than or equal to norm y minus x minus x. Now you just interchange the sign here. Okay, and this norm of y minus x we are assuming ct, and this just x as it is, and if t is large enough we can make it bigger than rho. Okay, so that's where this large enough, so this. Okay, so if t is bigger than this, then we also know that this norm y is bigger than rho. Again it will contribute only 0 values to the solution. Okay, and so that's what we write here. So thus for any x in R3 and t bigger than rho minus x, rho minus norm x by c, then we have u at t 0. Okay. So first we prove that for any t positive, uxt 0 if norm x is bigger than rho plus ct. And now we have proved if t is large enough, uxt is also 0 if norm x is less than ct minus rho. Okay. So for t large enough, the support actually lies in this annulus. Okay, so this is what I have written here. Okay, so this is the support of the initial data, closure of b rho 0. Okay, and at a later time t large enough, we have the support of u is only in this shaded region. So u is 0 inside here and u is 0 outside there. So the support is in the annulus. Okay, and this statement regarding the support is referred to as Huyghens principle. And physically, it's interesting to observe here. So the sound propagation is very well modeled by this wave equation, and we are in dimension 3. We are living in three-dimensional space. For the region, whatever I am saying, you will hear it after some time, and then you will not hear it again after some time. Okay, so it only lives for a short period of time. Okay, so otherwise we'll all be listening to whatever we have heard since long. Okay, so thankfully, so this sound propagation is very well modeled by this three-dimensional wave equation. Okay, so that's and this is in very much contrast with n equal to 2 case, where you do not have this Huyghens principle in the strong form. So this is the strong form statement. You have only Huyghens principle in the weak form. So that's the difference between n equal to 3 and n equal to 2, and that persists in all higher dimensions, n odd dimension and n even dimensions, though physically you don't have any example, but mathematically you will see that statement. So this support statement is different from n odd n and even n. Okay, that we'll see. Okay, so our next goal is to obtain the solution for the solution in 2D, and surprisingly we don't have to do much work, and so this is referred to as a method of descent, and this is due to Hadamard. So it's in fact called Hadamard's method of descent. So using the solution in n equal to 3, so that we have already derived, namely the Kirchhoff formula, we can obtain formula for n equal to 2. So for higher dimensions we can descend to a lower dimension. Okay, so unfortunately we cannot do this there is no method of ascent. So from n equal to 1 we cannot build, though we have used the case of n equal to 1 to derive solution for n equal to 3, but after much work. But here you see that there is absolutely no work. Just you use the formula for n equal to 3 and take some special initial data to derive the formula for the n equal to 2. Okay, and that's what we will discuss in our next class. Thank you.